In this module, we're going to introduce robust summary statistics. We're going to explain what we mean by robust, and we're going to define the median and the MAD. Let's start with a very simple illustration for this data that I'm showing you here. I randomly generated 100 data points from a normal distribution with mean 0 and standard deviation 1. And then I made a mistake on one of those measurements and it turned into 100. So you can see a voxel of the data has most of the data down here with means 0 and standard deviation 1, and then this one point way up there at 100. We in statistics call points like this outliers. They didn't come from the original distribution. They came from another process, in this case a mistake. Now what is the problem with this, with outliers? And these are common in high throughput measurement. The problem is if we want to compute using the observed data the mean and the standard deviation of our distribution, which in this case is 0 and 1, this one point is going to have a big influence on the sample mean of the average and the standard deviation. For this particular data set, if I compute these summaries, the sample average is 1.1, which is quite far from 0, and the standard deviation is 10, which is very far from 1. So one summary statistic that isn't as sensitive to outliers is the median. The median is simply the middle point of the data. It's the point that has half the data points below it, half the points above it. And it doesn't actually take into account what those values are, the values that are higher and lower. In this case, the median is 0.1, which is pretty close to 0. And the MAD, which I'm going to describe next, is 0.89, which is pretty close to 1. So what is the MAD? The MAD is a robust estimate of the standard deviation. For now, ignore this number here and let's focus on the right side of the formula. So what we do is we compute the median of our sample, and then we compute the distance of each point to the median. We compute the distance as the absolute value of the difference. Then we take the median of those deviations. That's where the name comes, median absolute deviation, MAD. We multiply by this factor 1.4826 to make this the summary statistic unbiased. On average, it's going to be equal to the standard deviation. Another robust statistic that we use is Spearman correlation. For this example, I created a data set in a similar way. I created two independent data sets, both with mean 0 and standard deviation 1, independent from each other, so no correlation. And then I made a mistake in one row where both measurements became big. So we see that point over here on the right. So if I compute the correlation of this data, it's 0.99. Why is it so big? Basically because this point here is driving the correlation to be high. Spearman correlation is a very simple idea. Instead of looking at the values, we look at the ranks. So over here on the right, we have the same data set, but now instead of plotting the values, I'm plotting the ranks. So this guy here is going to be ranked 100 and 100, and it's this point here. So it's no longer way out there and pulling the correlation up towards 1. The correlation computed on the ranks is just 0.066, much closer to the correct answer, which is 0 here. So again, very simple. You compute the rank of each vector and then compute the correlation. And that's Spearman correlation. So we've introduced the median, the MAD, and Spearman correlation as summary statistics that are robust to outliers. When we say robust, we mean it doesn't affect the measurement so much. So think about this point here. Imagine we made it 1,000 and 1,000,000. This value wouldn't change because the rank would stay the same. So why do we ever use the average, the standard deviation, and Pearson's correlation? So in genomics data where outliers are common, the median, the MAD, and other robust statistics are usually preferable.